Hello, good afternoon, everyone. I am Prashant Kumar from the University of Innsbruck in Austria, and today I'm here to talk about my project CFD in sanitary engineering. So, the overall aim of the project is to use dualist physics coupled with the biokinetic processes in order to simulate both the hydrodynamics and the digestion process within the anaerobic digester of a wastewater treatment plant. The biokinetics is the anaerobic digestion, and the hydrodynamics is basically referring to the mixing characteristics of the digester. The image on the right is of the digester in question, which is located in Siltal, quite close to Innsbruck. This is important because wastewater treatment is one of the ways to reduce the adverse impact our water consumption patterns have on the environment and to ensure a comfortable lifestyle for the future. And if not, then history has shown us multiple examples, such that of the Great Stink in London in 1858. The biokinetics. The anaerobic digestion is actually the decomposition of organic matter in the absence of oxygen, and it results in the production of methane and other byproducts. It has quite a few advantages. First is methane production. The second is that there is a reduction in the amount of waste to be processed, and which means that there is lesser transportation costs which the company has to be concerned with. And the third is that there is energy that the methane produced can be used for the production of energy, which is a lucrative option actually. So in order to model this process, we have something called the anaerobic digestion model. There were quite a few models proposed, but Angelo Ducky in 1999 proposed a very comprehensive model, and in 2002, Batstone with the IWA proposed something called the ADM number one, and based on the original works, but after multiple iterations and quite a few improvements made on the original model. So what this does, it considers the liquid phase, the gas phase, the physiochemical reactions, and the biological equations related to the decomposition, but all of these are calculated separately. ADM is quite nice, but what it lacks is that it makes certain assumptions. First is the homogeneity of the mixed liquor, or the homogeneity of the sludge, which is never the case. And second is constant temperature conditions. So the tank itself is temperature controlled, but there is never constant temperature. CFD, on the other hand, is well established to deal with these problems, and what we aim to do is layer these ADM results onto these CFD results. So for CFD, we have Eulerian and Lagrangian, but we chose Lagrangian or SPH here because we have because SPH has the possibility of using the inherent advection where the particles move to obviate the use of the complete transport equation. So in the transport equation, instead of modeling both the advection and the diffusion, we just have to model the diffusion. And the second is that there is easier simulation of free surface flows, because in these tanks it's not only just sludge but also there is some space for the gases produced. So we aim to use DSPH to simulate these hydrodynamics and to improve upon the previous simulations based on the changes made by the authorities. So there have been certain changes made to the original geometry and certain simulations which had been done of this tank, but they are not valid anymore because of there have been certain changes in the past few years. So this is the geometry here, and what we have is the total height of the tank is 24 meters. The diameter at the widest region is 15.4 meters, with a total capacity of 2,500 cubic meters. So this tank has an inlet and an outlet, and which has a constant feed rate of 0.95 meters per second. Under normal working conditions, this tank is not completely full. It's actually filled only to 22.9 meters. And there's a draft tube, as you can see from the image in the center, which helps in the recirculation of the fluid. So what it does is it takes in fluid from the bottom and releases it from to the top, which helps in mixing, and this has a constant flow rate of 1.5 meters per second. So the initial geometry that we just saw, these are the so we did dual S physics simulations, and we compared it with S phase simulations done previously and fluent results. So we have so the dotted line here are the S phase results, which is another dual SPH SPH code. The dashed is the fluent, which is an Eulerian method, and dual S physics is the solid line. So we can see quite a nice agreement between the three. Uh, and I would like to I would like to bring your attention to this region around the draft tube, which has a slightly higher velocity magnitude compared to the other regions. And because in the next simulation, which is without the draft tube, because what the authorities did was they had two tanks, as we saw, and from both of the tanks the draft tube doesn't work, and in one of the tank they actually completely removed it, and in the other the draft tube still remains but it's not working anymore. So we removed the velocity that was given to the fluid within the tank, and as you can see there is a much lower velocity, sort of a difference between the edges of the tank and closer to the draft tube. So without the draft tube, the only mixing criteria that this tank now has is, mixing help it gets is from the shape and from the inflow and outflow. And also there's another one which is actually the methane produced within the tank results in bubble formation, which helps in mixing. Um, and this comparison of the velocities can also be seen clearer here from this graph. So these are velocity profiles at 11.45 and 16 meters from the bottom, and the solid line, both of these represent the velocities with the draft tube, and the dashed lines are without the draft tube, and you can see how there is a substantial gap between the two. Velocity profiles are important to study to say something about about the overall mixing or the agitation, but what what we really want to worry about are these velocity zones. So the first one that we're going to talk about is the low velocity zone, which is basically the region within the tank which has a velocity of less of 10 millimeters per second to 1 millimeter per second, and you can see a comparison of when there wasn't a draft tube and when there was a draft tube. So these regions, what they have is like they're like the orange zone. They're not really dangerous to the tank, but there is substantially less mixing here, which is this is not really wanted actually. But and you can see that having the draft tube reduces these areas by substantial amounts. The second is actually dead volume. So now this is the red region. This is actually where, if we have these regions represented by purple, if we have these regions where the velocity is less than 1 millimeter per second, then what it means is that there is no movement, and can also, apart from affecting the methane production, there is a possibility of having sludge, of having sediment formation. So if there is sludge with high amount of total solids used, having this dead volume would mean that there would result in sedimentation and reduction, which would mean reduction in the overall usable volume of the tank, or usable capacity of the tank. And but what we can see from these images is that with or without the draft tube, it would not make much of a difference for this dead volume criteria. As a conclusion, I would like to say that ADM alone is not good enough uh, to model the total to model the total processes within the wastewater treatment plant. Neither is CFD, but together they form quite good. They can lead to promising results. The second is that the simulations that we saw, the initial simulations that we saw of with the draft tube, were in good comparison with the ones done by Masood et al. And the third is that the removal of draft tube results in a substantial reduction of the overall velocity of the fluid, but not so much of the dead volume. But we need to be sure. We need to. But I need to point out that this is not harmful as long as we do not use fluids with a higher total solids, which the authorities have started using. So after the removal of the draft tube, they don't use sludge which is prone to sedimentation, and we feel that the simulations are stable enough to be incorporated with ADM to model the biokinetics, which would allow for a better understanding of how such decisions affect the methane production. Thank you so much for your time, and if you've got any questions, I would be happy to answer. Thank you.